Given a number of queries, for what number of states is Grover's search algorithm most efficient? To answer this question, let's introduce some matrix representations. Consider the vector denoted by omega perpendicular. This has the matrix representation 1, 0. Also consider the vector omega. This has the matrix representation 0, 1. We can think of these as horizontal and vertical basis vectors. This omega denotes the target state. This is the target of our search. We are searching for this state using Grover's search algorithm. And this omega perpendicular is orthogonal to this state over here. Let's also define the state S. S is a uniform superposition of all of the computational basis states. And this omega perpendicular is very similar to S. The only difference is that omega perpendicular does not include omega. So with the exception of omega, these guys have all of the same computational basis states. The other notable difference is the normalization factor out the front. If you remove omega from S, you have to change the normalization factor to keep this state normalized. So S we can express in terms of these guys. We can express them as a linear combination. So we can express this as cosine of theta on 2 times this horizontal basis vector plus sine of theta on 2 times the vertical basis vector. Theta has an interpretation in the visualization of Grover's search algorithm, which I introduced in the previous videos. So this angle theta is very important in visualizing the action of the Grover iteration. We're going to use this matrix to actually construct the Grover iteration matrix. But first, let's construct the identity operator. So what does the identity operator look like for this matrix representation? So note that the Hilbert space that these states live in is n-dimensional. So it's a large Hilbert space in general. But what we're dealing with here is just 2-dimensional vectors. So that's because we're operating in a plane. And this plane is not the entire Hilbert space, but it is a plane that is very useful for visualizing the Grover iteration and the process that Grover's search algorithm undergoes. So let's write down the identity operator. So this is a symbol that's used to denote the identity operator. We can express the identity as a projector for this horizontal state plus a projector for the vertical state. And then the matrix representations of these outer products over here, they're going to be 2x2 matrices. So let's express them like this. We're going to have 1, 0, 0, 0 plus 0, 0, 0, 1. And when we add them together, we're going to get 1, 0, 0, 1. This is the 2x2 identity matrix. And you can break that identity matrix up into a horizontal projector and a vertical projector. So this projects onto this omega, and this projects onto the vector that's perpendicular to omega. Or in other words, instead of saying perpendicular, we could say orthogonal. That means that the inner product of omega and omega perpendicular is 0. And you can see that by performing matrix multiplication of the bra version of this and the cat version of this. Everywhere where you have a 1, you have a 0. So here we have a 0 and here we have a 1. So that means the product of all of those terms is going to be 0, so they're going to sum up to 0. So that's how we would evaluate the inner product. Now that we have the identity operator, let's introduce the unitary operator U omega. So U omega has the form of the identity minus 2 times this projector formed from the omega vector. So what does this look like in the matrix representation? we're going to have the identity matrix minus 2 times this projector, which is 0, 0, 0, 1. So what does this do? Well, we have a minus 2 over here, so that actually flips the sign of this term. And that gives us the matrix representation 1, 0, 0, minus 1. And this looks just like the Pauli Z matrix. But keep in mind, we're not dealing with a two-dimensional Hilbert space. We're just using these two-dimensional vectors to visualize something that's going on in a plane. So this is not the same as the Pauli Z operator acting on qubits, but the matrix representation is the same. So this has the effect of negating the vertical component. It negates the component of a vector that's along the omega direction. So this is the vertical direction. All it does is it flips the sign over here. So now we have U omega. And U omega can also be thought of as the oracle. What we have over here is a quantum oracle. We're encoding information that tells us which of the states that we're searching in our database, which of those states satisfies the criteria. And the state that satisfies the criteria is the state omega. So U omega actually marks that state, and it marks it as the target. So this is really important. It flips the sign, and this minus sign is a way of marking that state and identifying it as the target of our search. Next, let's introduce the outer product of S with itself. So we have S in this combination. So this is a ket-bra combination. That's the same combination that we have over here. We have ket-bra, ket-bra, ket-bra. And when you have ket-bra, that's an outer product. So that's how you turn these vectors into matrices, these 2x2 matrices. They are square matrices. But if you swap the order and you had a bra-ket, that would be an inner product. And the output of an inner product, that can be evaluated as a complex number. So those are completely different objects. So the order is very important. So what is this going to be? Well, we can write this ket as a column, just like we have these columns over here. So we're going to have a column, and the entries are cosine of theta on 2, sine of theta on 2. That's just another way of writing this representation over here. We have a coefficient for this horizontal vector, and we have a coefficient for this vertical vector. And these coefficients are written in terms of the angle theta. So this is the ket, and now we need a bra. So we have to take the transpose, and we also have to take the complex conjugate. But all of these coefficients are real numbers, so the complex conjugate has no effect. So we're just going to have cosine of theta on 2, and then sine of theta on 2. So those are two entries in this row vector. So now that we have this combination, we can form a matrix. And that's a 2x2 matrix. So first we need to take this cosine and this cosine, and that's going to give us a cosine squared of theta on 2. And then let's consider a mixed term. We're going to have sine and cosine. So sine of theta on 2, cosine of theta on 2. And let's also consider another mixed term, which is in the off diagonal. So that is also sine of theta on 2, cosine of theta on 2. And then finally, let's consider this sine and this sine. That's going to give us sine squared of theta on 2. And we can put these brackets around because this is a 2x2 matrix. So what is this going to give us? Well, we can use some trigonometric identities. And we can pull out a factor of 1/2. So if I pull out a factor of 1/2, then I can write this as a matrix. So first, I'm going to turn this cos squared of theta on 2 into 1 plus cosine of theta. And I'm going to turn this product into sine of theta. So note that this half over here can be distributed back, and that's going to give you an equivalent expression. These are just trigonometric identities. And up here, we're also going to have sine of theta, and then we're going to have 1 minus cosine of theta. So this sine squared only differs from the cosine squared by a sign over here. We have a minus sign on this cosine. So that is the matrix representation of this projector formed from S. And remember that S is a uniform superposition of all of the computational basis states. So now what we can do is we can define the unitary operator U sub S. And this is going to have the effect of reflecting states over the S axis. So if you draw an imaginary line that goes through the S vector, we're going to reflect over that axis. And we're still going to remain in the same plane. We're going to remain in this plane that is spanned by these two vectors. So let's write this. This is going to have the form 2 times this projector formed from S minus the identity. So what is this going to equal? Well, if we multiply this matrix by 2, that's going to get rid of this 1/2. And if we subtract the identity, we're going to subtract 1s from the diagonal. So that's this matrix over here. We're going to subtract 1 along the diagonal. So we're going to get rid of this 1, and we're going to get rid of this 1. And what is the matrix going to be? Well, then we're going to have cosine of theta, sine of theta, and we'll also have sine on theta up here. And we're going to have minus cosine theta over here. So this is the 2 by 2 matrix that we're dealing with. So there's just a minus sign on this cosine. And next, what I want to do is define the Grover iteration. So the Grover iteration is the product US U omega. So this means first apply U omega, then apply US. So how are we going to get this matrix G for the Grover iteration? Well, we just need to multiply the matrix representation of US and U omega. So that's this one over here. And what is this minus sign going to do? Well, it's just going to flip some signs in this matrix. And it's going to give us the matrix cosine of theta, sine of theta, minus sine theta, and cosine theta. So instead of having a minus sign down here, we have flipped the signs over here, and now we have a minus sign up here. So that is what happens when you multiply this matrix and this matrix. So now we have this Grover iteration matrix. But can you notice that along the diagonal, we have cosine of theta, and on the anti-diagonal, we can identify another combination. So we can actually write this as cosine of theta times the identity matrix. So we have the identity matrix, and we're multiplying cosine theta. And then we can also identify minus I sine theta times the Pauli Y matrix. So can you see that the Pauli Y matrix has entries I and minus I over here? So now if we take this minus I and we multiply it by I, we're going to get plus 1. And if we take minus I and we multiply by minus I, we're going to get minus 1. So that explains these signs over here. That's why we have a plus and a minus. So, and then we can also factor out the sine of theta. So this is equivalent to this matrix representation. And this form over here can also be written as a matrix exponential. So I'll write that, actually I'll write it down over here. So we're going to have e to the minus I theta y. So this is another way of writing this expression. And I have a few other videos in the quantum mechanics playlist where we actually show these rotation matrices, and they come from the Taylor series expansions. So if you take the exponential of a matrix, you can write that as a Taylor series. And you can identify terms in that Taylor series that match the Taylor series for the cosine and the sine. And then you can pull out some coefficients, rearrange the order, and you can show that these are mathematically equivalent. Now that we have this matrix representation of the Grover iteration, we can write down another interesting relationship. So if we take this G and we apply it R times, so this is the number of iterations. We can also think of it as the number of queries. If we take this matrix and we apply it to S, what are we going to get? Well, this is exactly the same as this operator, e to the minus I, but instead of theta, we have to apply this r times. And we can use exponential rules to take that exponent of r and move it in and just multiply by r inside this exponent. And then we have to apply it to s. So what is this equivalent to? Well, taking this power of r is the same as just scaling this theta by r. So we can also put that back into this matrix representation, and that's going to give us cosine of r theta, sine of r theta, minus sine of r theta, and then cosine of r theta. So you can see what has happened to this matrix. This matrix is the same as this matrix raised to the power of r. And raising this matrix to the power of r is the same as multiplying this angle by a factor of r. And we can see that by writing this in terms of this exponential of this matrix. So the matrix that we're dealing with here is the Pauli Y matrix, and these guys are just coefficients in this exponential. And what about this s over here? Well, s is the same s that we're dealing with here, so we can write that as cosine of theta on 2, sine of theta on 2. Now let's perform this matrix multiplication. That's going to give us cosine of r theta times cosine of theta on 2. And that's our first part. And then the next part is going to have this minus sign. So we're going to have minus sine of r theta, sine of theta on 2. And what about this term over here? We're going to have sine of r theta, and that's going to scale cosine of theta on 2. And then we can add to that cosine of r theta times this sine of theta on 2. And now we have applied this 2 by 2 matrix to this column vector, and that's given us another column vector. But this form is a little complicated. So let's rewrite this using a trigonometric identity, and that's going to give us a simplified form. So here we have cosine of an angle times cosine of another angle, and then we're subtracting sine of that angle and then sine of that other angle. So what is this equivalent to? This is equivalent to cosine of the sum of these angles. So all of this big mess is equivalent to just one cosine, and then we have this angle plus this angle. And you can see there's a common factor of theta, so we can pull that common factor of theta out, and then we have 1/2 plus r. And what about this bottom part over here? Here we have sine cos plus cos sine. So this is equivalent to sine of theta plus 1/2 times 1/2 plus r. So this is equivalent to this. And you can verify all of these trigonometric identities by rewriting the trigonometric functions in terms of complex exponentials. And then those complex exponentials are easier to manipulate. You can multiply them, add them, and use the exponent laws, and you can verify that these trigonometric functions are equivalent. So you can verify all of these identities. So the reason that I've put it in this form is because in this form we can very easily read off what is going on. If we apply this Grover iteration, r times, to the state s, what is that going to do to the state s? Well, the state s begins with this 1/2. So if we set r equal to 0, then we just have that theta on 2. But then what we're doing is we're adding r copies of theta. So each Grover iteration is a rotation by the angle theta. So that is why theta is a very useful quantity to define. It has a very intuitive interpretation in the visualization of Grover's search algorithm. Now that we have this matrix representation, let's write down some ways of calculating the probability. So first, let's write down the initial probability of measuring omega. So we can quantify that by writing the inner product of, so we're going to have omega, and then 0 applications of this Grover iteration. So we haven't applied it at all yet. And then we're going to take s over here, and let's take the absolute value squared of this. this is going to give us the inner product of S with omega. So omega is this vertical vector. And if you take the inner product of this, if you turn it into a bra, and then act on this vector, where r is equal to 0, you're just going to pull out this value. And then if you take the absolute value squared, that's going to give you sine squared of theta on 2. And this is actually equivalent to 1 over big N, where this big N is the number of states. So this is at the beginning. At the beginning, if this N is really large, we have a very small probability of measuring the target state. But then after we apply r iterations of Grover's this Grover iteration, what is that going to give us? Well, this inner product is going to change. So we're going to have the inner product of omega with g raised to the power of r, and then we're going to have s, and then we're going to take the absolute value squared to get the probability. And what is that probability going to be? It's going to be equivalent to, we're going to have this object over here squared. So we're going to have sine squared of theta times 1/2 plus r. And we want to find the value of r which maximizes this. So we want this to be approximately equal to 1. And a probability of 1 means you have a 100% chance of measuring the state omega. So you can see what we're doing with Grover's search algorithm. We are starting in this state S, so this uniform superposition, and we have a 1 over n chance of measuring the target state. And then we are amplifying that probability and we are getting it close to 1. And this is going to be the goal. So what value of this argument, of the sign, is going to guarantee that we get a probability that is approximately equal to 1? We need this to be roughly equal to pi on 2. So I'll write that down here. So what we need is theta times 1/2 plus r to be approximately equal to pi on 2. So everything up to this point over here has been exact. We're dealing with exact multiplication of matrices, and the only point where we have introduced an approximately equal to sign is over here. We want something to be approximately equal to 1. And after this point, we're going to be dealing with approximations. So we're going to see how we can approximate a relationship between this r, the number of iterations, and this big N. So let's see how we can do that. We want this to be roughly pi on 2, so that we get something that's close to 1 over here. How can we guarantee that? What value of theta do we need? Well, we can write another relationship over here. We can write this as theta is equal to pi over 2r plus 1. So you can see if I just divide by this coefficient, that's going to give me pi on 2r plus 1. Then another interesting thing that I can do is I can take this relationship over here, and we've seen that relationship in previous videos. If you take the square root of both sides, then you get 1 over the square root of n. And that is actually the normalization coefficient in S. So because you have capital N computational basis states, you have to divide by a normalization coefficient, and that normalization coefficient is 1 over the square root of n. And because we are finding the probability, we have to take the square of that, and that gives us 1 over n. So now that we have this relationship, we can take the reciprocal. So that means n is equal to the reciprocal of sine squared, which is actually the cosecant squared. So we can write this in an abbreviated form, CSC, the cosecant squared of theta on 2. So this is exactly equal to this. But now what we want is an approximation. So this approximation is going to come by substituting this approximate value of theta. So if we substitute that inside, we're going to get the cosecant squared of pi over 4r plus 2. So this is the argument of this cosecant squared. And this is an approximation for the value n, which guarantees that this is approximately equal to 1. Now let's actually see some values. So let's create a column over here. We have a column for r, and this is actually going to be a column that tells us what value we're dealing with. And along this row, we're going to have values of r, and then we're going to have n over here. So given a number of iterations or a number of queries, what value of n is most efficient? We're going to use this relationship to work that out. So let's write down some values over here. Let's consider 0, 1, 2, 3. And what values of n are we going to get? So for 0, we're going to get 1. For 1, we're going to get 4. And beyond this point, we're no longer going to have exact solutions. We're just going to have approximate solutions. So this is going to be approximately 10. This is going to be approximately 20. And if we keep going on, if we go up to a really large number, like 10 to the 3, so we have 1,000, this is going to be roughly 1.62 times 10 to the 6. And if we continue this pattern, imagine 10 to the power of p, where p is some power, some integer power. So what is this value going to be? Well, it's going to be approximately 4 on pi squared times 10 to the 2p. Where is this coming from? Well, this coefficient and the fact that we have to square this power, that is coming from the relationship that we derived in a previous video. So we had a relationship where for really, really big values of n, so if n is much bigger than 1, we had that the number of iterations has to be approximately equal to pi on 4 times the square root of big N. And this guarantees that we have a value that's close to 1 for this probability at the end of all of the Grover iterations. So this is what the limit is for really, really big N. And if you invert this equation, you can see that if you take the squares of both sides of the equation and you multiply by the reciprocal of this coefficient, you're going to get this relationship. So for really, really big values of R, this is the optimal value of N. And you can see that this is the reason we're even considering this quantum search algorithm, because of the advantage over here. So if you have a really, really big number of states, you have roughly the square root of queries required to find the actual number, or the actual state that you're looking for. So that is the advantage of using Grover's search algorithm. And you can see that beyond this point, you just get approximate solutions. But these guys are actually integers. And this one is very special. This one is 2 to the power of 2. That corresponds to a 2-qubit system. And there's another video in the playlist that is dedicated to describing this 2-qubit example of Grover's search algorithm. But what is this? What is this r equals 0 option? So r equals 0 means you don't apply Grover's iteration at all. And this value of 1 means that you only have one state that you're searching for. So this can be considered the trivial case over here, because you only have one option. And if you only have one option, then you've already found the solution. So this is not a very useful option. This is the first option where you actually have something useful. You have 4 different states in your sample space, and you're trying to search for one of them. And you can see that this option over here, this actually provides some advantage. And as this gets larger and larger, we tend to approach this value over here. So this is in the limit of really, really large values of n. So what does this relationship actually tell us? It tells us for a given value of r, what the optimal value of n is. And what is this r actually telling us? This r is telling us how many times we have to apply Grover's iteration. And every time we apply a Grover iteration, we have to call this query. We have to call that query once every time we apply this matrix over here. And that has the effect of producing that rotation in our visualization in the plane. So hopefully this video was helpful in understanding how we can optimize quantum search.